It took humanity decades of engineering and billions of dollars to accelerate protons to 99.999991%, the speed of light, inside a 27-kilometer ring. A black hole containing 6.5 billion solar masses has been firing plasma at over 99% light speed across 18,000 light-years, using nothing but magnetic fields threaded through its own spin. Your particle accelerator has a parking lot. The Large Hadron Collider at CERN accelerates protons to 99.999991%, the speed of light, inside a 27-kilometer ring. And physicists celebrate that as our greatest engineering achievement. Nature does the same thing continuously, at a scale billions of times larger, using nothing but gravity, magnetism, and the violent physics of a supermassive black hole. This video traces exactly how that happens, what it looks like when the geometry of spacetime makes those jets appear to break the ultimate cosmic speed limit, and why the most recent Chandra observations, published in June 2026, have just rewritten what we thought we knew about the structure inside these jets. The fastest natural object, confirmed by direct observation, is a plasma jet fired from the supermassive black hole at the center of the galaxy Messier 87, which sits 55 million light-years from Earth. NASA's Chandra X Ray Observatory has confirmed that particles inside this jet are moving at over 99% the speed of light. To feel that number, consider this. Light takes just over 8 minutes to travel from the Sun to Earth. A particle in the M87 jet covers that same distance in roughly 8 minutes and 5 seconds. Voyager 1, the fastest spacecraft humanity has ever launched, would need about 17,000 years to cover that same Earth-Sun gap. The jet itself extends 18,000 light-years outward from the black hole, a physical structure so long it would dwarf the distance from Earth to the center of the Milky Way. And this is not a brief eruption. The jet has been firing continuously for millions of years. The question is, what force is powerful enough to sustain it? The black hole at the center of M87 is 6.5 billion times the mass of our Sun. Nothing in the observable universe comes close to that kind of gravitational grip. But gravity alone does not create the jet. As gas and dust spiral inward through the accretion disk, they form a superheated plasma that generates magnetic field lines coiling like a cosmic spring. Those field lines thread through the rotating black hole, and through a mechanism called the Blandford's-Najac process, they extract rotational energy directly from the black hole's space-time. That energy is channeled into two opposing beams of plasma, launched perpendicular to the accretion disk at velocities approaching the cosmic speed limit. The power output of these two jets combined rivals the luminosity of an entire galaxy. For comparison, our most powerful particle accelerator, the LHC, delivers about 14 teri-electron volts of collision energy. The energy carried by 1 second of the M87 jet would power every city on Earth for roughly 100 billion years. But nature does not stop with M87. In June 2025, Chandra found something even more extreme. In June 2025, astronomers presented Chandra findings on two quasars designated J1405+0415 and J1610+1811. Located 11.6 and 11.7 billion light-years from Earth. These black holes existed at what cosmologists call cosmic noon, a period roughly 3 billion years after the Big Bang, when galaxies and supermassive black holes were growing at the fastest rate in the universe's history. Their jets extend over 300,000 light-years, 3 times the diameter of the entire Milky Way. Chandra measured the particles inside the first jet, moving at between 95 and 99% the speed of light. The second jet carries roughly half the total energy output of all the hot gas orbiting that black hole. What makes these jets even detectable across 11 billion light-years is the cosmic microwave background itself, the faint afterglow of the Big Bang, which was far denser then and acted as a kind of energy amplifier, boosting the X-ray signal enough for Chandra's optics to resolve it. The universe, in this case, used its own echo to illuminate the fastest things inside it. Here is where the physics gets genuinely strange. When radio telescopes trained on blazar jets, a class of galaxy with a jet pointed almost directly at Earth, they measured something impossible, features moving at over 25 times the speed of light. Scientists using the Very Long Baseline Array tracked 3 blazars between 7 and 9 billion light-years away, and the measured apparent speeds exceeded 25 c. Nothing in Einstein's framework allows that, except the measurements are not wrong. They are an illusion produced by relativistic geometry. When a jet fires plasma almost directly toward you at 99.9% the speed of light, the light emitted later in the sequence has almost no extra distance to travel compared to light emitted earlier. The time gap between those signals collapses. To an observer, the object appears to cover enormous distances in almost no time, producing an apparent velocity that violates the cosmic speed limit. The jet has not broken physics. It has exploited a loophole in how light reaches us, one that makes a real speed of 99.9% light appear on our instruments as 25 times light speed. That apparent speed, by the math, corresponds to an actual Lorentz factor of at least 25 to 30. In June 2026, an international team led by Camille Poitras at Laval University published the most detailed X-ray view ever obtained of the M87 jet, combining 13 years of Chandra observations spanning 2012 to 2025 with advanced image processing algorithms. For the first time, structures that had been blended together by previous imaging were resolved as distinct, independently moving features. What they found was not a smooth, uniform beam. Inside the jet, some bright knots remain nearly stationary for years, anchored by magnetic pressure. Others accelerate outward at apparent speeds approaching 5 times the speed of light. Those knots are not random turbulence. They are sites where faster plasma slams into slower plasma, generating powerful shocks that re-accelerate particles and produce intense bursts of X-ray emission. The jet is not simply a cannon. It is a series of nested acceleration stages, each one passing energy forward like a relay. These shock structures had been predicted by computer simulations for decades. June 2026 gave us the first direct X-ray confirmation that they are real. If M87's 5 billion solar mass engine feels large, consider what Tone 618 implies. That black hole, the most massive confirmed in the channel's previous episode, clocks in at 66 billion solar masses. A jet powered by a black hole that size would dwarf the M87 beam the way M87 dwarfs a stellar mass black hole. Relativistic jets scale with the mass and spin of the central engine, meaning the most extreme jets in the observable universe may be associated with ultramassive black holes whose hosts we have not yet resolved. When a jet from an object like Tone 618 fires outward at 99% the speed of light across a 300,000 light-year span, it does not merely travel through its host galaxy, it reshapes it. The jet heats the surrounding gas, suppresses star formation, and carves tunnels through the intergalactic medium that can persist for hundreds of millions of years. The fastest object in the universe is also a terraformer at galactic scales, and the energy it deposits is one of the reasons some massive galaxies stopped forming stars while the rest of the universe was still building them. That energy budget changes everything we think we understand about how galaxies evolve. For all the precision of Chandra, all the baselines of the VLBA, one core question about relativistic jets remains genuinely open. We do not fully understand how the plasma is collimated from a chaotic 100 million degree accretion disk into a beam narrow enough to stay coherent across hundreds of thousands of light years. Simulations produce jets, observations confirm jets, but the exact magnetic geometry at the base, within a few Schwarzschild radii of the event horizon itself, is still beyond even the Event Horizon Telescope's current resolution. The 2026 Chandra data showed us the shock structure in the outer jet with unprecedented clarity, and that structure matches simulation. But the ignition point, where the energy is extracted from curved spacetime and first organized into a coherent beam, remains one of the open frontiers of high-energy astrophysics. The fastest sustained phenomenon in the known universe is simultaneously one of the least understood. Every observation that brings us closer to the base of the jet tightens the constraints on that mystery, and the next generation of X-ray observatories is already being designed to close the gap. The fastest sustained thing in the observable universe is not built, launched, or steered by anyone. It emerges from the same physics that makes a black hole inescapable, turned outward, across distances that would take Voyager longer than the current age of the universe to cross. Something else has crossed interstellar space at a significant fraction of the speed needed to escape a star, and unlike the M87 jet, it was small enough to fit inside a football stadium. That object was called Oumuamua, and what it was is a question science has not yet closed.